hope you had a lovely Wednesday. Man, it was hot. It's supposed to be a little bit cooler today. Ha, we'll see. All right, where am I? I'm here. There we go. So we need to talk about yesterday's calculations. And, the example problem is very much like one of the ones we already did, and it's also really easy to Google it on the internet, but I hope that you tried it on your own. And we're going to go over some quick notes and then start talking about the lab we're going to do. Again, you're going to need to have, those of you in the classroom, closed-toed shoes or socks to put over your toes, or $1 for the surgical room booties. Those are reusable. So for the next several days, so Friday, Monday, Tuesday at least, we'll be doing little bits of this lab. It's multiple different reactions. And so, and you can reuse these things, okay? They're not perfect. They don't, they shed water and, they don't absorb it like socks would. So that's actually preferable to have those if you don't have closed-toed shoes, but be prepared. I can't let you do the lab if you don't have them, okay? So please, please, please do. All right, I'll try and remind you tonight too. Would it be better tonight or tomorrow morning to send a reminder? I may say morning. I may say night. Oh, heck. Okay, I'll try and do both. You guys are difficult. Okay, not really. I wanted to. So has everybody submitted the calculations? It's going to submit the calculations? Because I'm going to show you the answers. And if I show you the answers, then you're not going to get full credit. You're not going to get, you'll get half credit at best if you turn it in. Okay, so let me find my answers. Let's see if I can find them. Boop. Boop. Next. A minute. And I'll try and make it big. So the question gave you percents for each of the elements, carbon, hydrogen, and oxygen, and gave you the molar mass of the compound. And again, we really already did this problem, but that's okay. 40% carbon, so you just make it 40 grams, 6.71% hydrogen, make it 6.71 grams, 53.29 grams of oxygen. Carbon's molar mass from the periodic table, 12.01, hydrogen 1.01, oxygen 16. And so you'll notice that carbon and oxygen come out to both be 3.33. That means when you divide by the smallest number, their number, they both come out to be 1. And the 6.64, and again, if you did it to the hundredths, it doesn't come out perfectly even. So 1.994, close enough to 2, right? We can round that much, 6 thousandths. So the empirical formula is 1 carbon, 2 hydrogens, 1 oxygen. If we calculate the molar mass for that molecule, it comes out to be 30.03. Take the known molar mass for the molecular formula, divide by the empirical formula's molar mass, and you get 2. So you double all the subscripts. C2H4O2 becomes the molecular formula. So it's a lot of work. There's a lot of work involved in doing these calculations. And you have to remember to change things and divide by stuff. And it's not, pretty short question, but a pretty long answer. Okay. So hopefully that made sense. Does anybody have any questions on that? No? Everybody's good? Okie doke. So we're going to go ahead and move forward. And this is the note sheet. We've watched the Hindenburg. Oh, I was going to show you the picture. I wonder if I can find it fast. I was going to show you how bright blue that was. I bet I won't be able to find it very fast. Let's see. I don't think it was last spring. Let's go back one more year. You can see all my family pics, my broken ankle. Shoot. Shoot, I wonder. Let's see if I got this. No. I'm not going to find it. I'll look for it later. The Remsen demonstration, and hopefully I'll turn that in. So we're going to talk about how we write chemical equations. You've seen them already. You know this stuff. It's really not that hard, but let's go through it and make it formal and put it into your brains. And how many are going to prom? Everybody doing that? Hopefully it's not too bad out on the parking lot at Chicken Ranch. I have not been there in ages, so I know they redid a lot of stuff. Is it? Huh.
I think they're doing it where they do the drive-in movies.
Oh, okay. Mask over your face, please. So how are they going to make it work for like bathrooms and stuff? Or are you guys going to be able, are you going to be? Yeah, they said the DJ is going to be in the middle. Okay. And yeah, it'll be interesting. Why is this not opening? Oh, I thought we were having a good day. Come on, PowerPoint. There you go. All right, so this is what we observed yesterday or Tuesday. Okay, so what's happening in this process is the nitric acid and the copper react to form copper 2 nitrate. And then you make that nitrogen dioxide gas, that brown gas. And there's also water forming. You can't really tell because it kind of gets incorporated in with the green stuff. It dissolves the copper 2 nitrate. And then when the water rushes back in, we end up with free copper ions. That's the blue color, and the nitrate ions. It dissolves it completely. So, and that's because of the acidic nature of the water that was in the beaker. Remember, the phenolphthalein turned from pink to clear. That's an indication that you formed an acid. All right, so writing chemical equations, what do we do? As you saw on the video yesterday, if you did it, reactants are on the left, products are on the right. And that's, you know, kind of like how we do. We read from left to right in this country, so it kind of makes sense, okay? So in terms of a recipe, which we'll use the term sometimes, the ingredients are on the left and the stuff. What's the word I want? Food. No, I don't want to do it that way. The recipe. So it's like, you know, if you're making something, you got the cookies are on the right. So if you got flour and sugar and butter, you make cookies. So same thing. We use the arrow and not an equal sign. Okay. So that's a really important concept also. Sometimes there's multiple reactants. Sometimes there's multiple products. Sometimes there's both. So there's not always more than one reactant. Sometimes there's just one. And sometimes there's just one product, but not always. Okay. The reaction between methane gas and oxygen is a combustion reaction. We'll learn about all these types of reactions. And the only two products in perfect combustion, which nothing's perfect, are carbon dioxide and water. Now, for us up here on the foothills, we don't have methane. Remember, methane, CH4, we have propane. Okay, if you have gas at your house. All right, but in big cities or, you know, small cities, places that have soft ground and lots of people, they have methane piped in. This is a rusting car, so sad, so bad. I'm a little Volkswagen Bug, and it's iron. Of course, steel is mostly iron, so it's depends on what kind of steel, if you recall. But the main ingredients in steel is iron. So there'll be a little bit of carbon. There might be some other elements in there as well for strength, etc. Remember from our talk on alloys. When the oxygen in the air reacts with that iron, it makes rust, which officially is iron with a Roman numeral 3 oxide. So we know it's iron and oxygen. And that 3 says that the iron has a +3. We know oxygen's always a -2. And so when you do the crisscross, iron 3 oxide or rust is Fe2 sub 2O3. And again, we'll get to going over how we do all that soon. Okay. And then this really gross picture is a picture of someone with a cut on their knuckle. Owie, owie, owie. And then all these bubbles. And so most of you probably have hydrogen peroxide at home in your bathroom. Anybody? Brown bottles. And that is can be used like to lighten your hair. It's the bleach, quote unquote, that they use for hair coloring processes. But some people use it for mouthwash. Some people put it on cuts. And the reason why this works is because when it decomposes, it makes water super easy, and it makes oxygen gas. So hydrogen peroxide is H2O2. That looks really familiar, right? It's almost like water. And when it falls apart due to sunlight or contact with your skin, for example, you can make water and oxygen gas. And you guys know from biology that most bacteria are anaerobic, which means what? They don't need oxygen. Okay, they don't. Aerobic, right? Aerobic exercises means you need more oxygen. Anaerobic means no oxygen. So if you put this on your cut or use it as a mouthwash, the oxygen smothers the bacteria or can. Okay, so the bubbles are oxygen gas forming. And we'll do a little reaction with that. It's kind of fun. All right, so there's different kinds of equations. The book lists out word equations. This is when we use the names of the elements or compounds that are involved with the reaction. So sodium metal and chlorine gas makes sodium chloride. And so in your head, I hope you're seeing things like, oh, sodium, that's Na. Chlorine gas, oh, chlorine's a halogen. It's diatomic, okay? And you all, I'm sure, can visualize sodium chloride for salt and NaCl, okay? So this is a skeleton equation. It has all the correct symbols and formulas for the chemicals that are involved. However, it's not balanced, okay? So words have words, surprisingly. Skeleton equations have symbols and formulas. And from there, we learn how to balance them. And then there's some other symbolization that goes into equations, because even if you have the right ingredients, the right reactants, they may not react unless they're in the correct state. Okay, so we're going to learn about what these little symbols mean. And I've used these before and I've talked about them, but, you know, not formally, so we're making it formal today. What do you think little s means? Guess. What do you think little g means? Yes. Perfect. All right, so the blue numbers out in front are what we call coefficients. Okay, we have to have the right number of pieces accounted for on both sides. Remember, a balanced equation has to have the same number of atoms on each side. We can't create or destroy matter. That's the law of conservation of matter or mass. Okay, so on this side, I've got 1 sodium and I've got 2 chlorines. On this side, I have 1 sodium and I have 1 chlorine. That's not balanced. Okay, so we throw in the coefficient of 2. And if we put 2 here, then we have 2 of these pieces. Now we have the same number of pieces on both sides and we have a balanced equation. Okay, but you have to remember that chlorine is diatomic and that will come up. So is oxygen, so that'll really mess people up if you're not careful. All right. already went over that. All right, so this is out of your textbook, but again, these are symbols that you need to know. Plus, I mean, it's pretty obvious, I think. You're adding things together, or they're both there. Always remember that for the arrow, it's not equals, it's yields, it's produces, forms, generates, makes, okay, but not equals. All it does is separate what you're starting with and what you're ending with. Sometimes, like you saw in the video, also there's what we call reversible reactions, and they can go back and forth between products and reactants depending on the concentration of each. There's a whole lesson and lab to do on that. There's something called Le Chatelier's principle, and we are not going to get to that this year, but you'll probably encounter it in college. A little S is for solid, as you said, a little L for liquid. And again, because lowercase l on a periodic tables, the font that they've chosen to use, it looks like a capital I because they don't put the top and bottom on the I. Same thing with the lowercase l. They've got it in italics, but I like to do a cursive lowercase l just to make it clear. Little g for gas, and then AQ we've talked about before. It means aqueous. It means it's dissolved in water. Okay, so AQ is aqueous. Lots of things have to be dissolved before they react. All the reactions in your body, all the chemical reactions that keep you alive, happen in solution. Okay. You're mostly water, right? Everybody knows that. Okay. And then another little thing that we sometimes put over the arrows is we indicate that heat has to be added. So the delta symbol is for change, but it also is incorporated. There's something called delta H for enthalpy. It's how much energy is taken in or given off during a reaction. And so that's used here. Sometimes we write the word, but we kind of don't like words in chemistry. We like symbols and shorthand things. So delta is usually used. And then the other thing that will go over the arrow occasionally is if you need a catalyst. And platinum, for some weird reason, is a really good catalyst for a whole bunch of reactions. In your catalytic converter in your car's exhaust system, the little beads that are in that are coated with platinum. And that helps speed up the breakdown of the nasty crud that's coming out of your engine into less nasty crud coming out your tailpipe. And so platinum's used in other reactions as well. It's really strange. It's in, the column with nickel, palladium, and platinum. Yeah, it's used for a lot of things. But there's other kinds of catalysts. We'll use something called manganese dioxide for a catalyst in our hydrogen peroxide reaction. Okay. All right. Questions on symbols? Okay. All right. So this is going to be similar to what you're going to do. You're going to have a test tube with some hydrogen peroxide in it. And we're going to put this black powder in it, this manganese dioxide stuff, and it's going to bubble. And that bubbling is caused by the breakdown of the hydrogen peroxide into water and oxygen gas. And it also generates a lot of heat. It's what we call exothermic. So catalysts speed up reactions without being incorporated into the products. Okay, you get to cycle them again. You can retrieve them and reuse them over and over and over again. They're not used up. In your body, what kind of compounds are catalysts to speed up reactions in your body, like digestion? Enzymes, good job. So enzymes are biological catalysts. And I do this for enzymes, but you can, it's not New Zealand. Anyway, enzymes equal biocatalysts. Okay, they're not used up, they're not really part of the reactants or the products. They're just making it go faster. You guys know if you eat food, if you didn't have enzymes, you die before, because nothing would get digested in time to keep you alive. It's kind of weird. All right, balancing equations. I already kind of mentioned this. You got to have the same number of pieces on both sides of your equation. Law of conservation of matter has to be followed. And so, well, that's really small. Oh, it's because of the pictures, I forgot. So if carbon and oxygen go together to make carbon dioxide gas, very nicely, this is already balanced. Okay, there's one carbon on the left, two oxygens on the left, the reactant sign, one carbon with two oxygens on the right. That doesn't always happen. Okay, so, you know, we can make carbon monoxide as well, and that's going to require some coefficients. Right, so whatever you've got on the left has to be present on the right. End of story. I feel like I was going to say something, but oh well. All right, so the first thing you got to do to write a balanced equation is write the skeleton equation. They may give it to you. They're probably going to give you words. And this is where those of you that put the time in earlier in the semester to learn how to write ionic compounds and molecular compounds, it will pay off. Okay, so you write your skeletal equation, and then you add in those coefficients to make sure the number of atoms of each element on both sides is equal. One huge hint that I'm going to give you that I wish I had known when I was in high school and college is when you have something like copper nitrate, copper 2 nitrate, don't break apart the polyatomic ions. Leave them as a little unit because they're going to stay as a little unit. They're going to dissociate, but the nitrates are going to stay as little packages. Okay, so don't break it in. Don't make a list. One of the things I used to teach you years ago, which is really dumb, is, oh yeah, put the copper, put the nitrogen, put the oxygen, okay? And then count up how many atoms. Don't do that. Leave the polyatomics in their little bundles. So I made you learn your polyatomics, and we had quizzes on them and all that. You're going to get to use that list. You guys still have your list of polyatomic ions somewhere? So you'll be able to make use of those. I'm not going to make you have to remember them going forward now. But if you want, I'll try and remember to put that back into the materials. Let's look really fast. Did I already put it in the materials? I think I did. Oh, okay. Something in my eyeball. Let's get down here. Periodic table, rules for sig figs, calculator, first semester, lab format, lab equipment. Oh, I don't have the ion list. Is the ion list here somewhere? Oh, periodic table of ions, but that's not polyatomic ions. Okay, I should have looked that up earlier. Let's see. Was that last semester or this semester? It was this semester. Monatomic ions, polyatomic ions, all the way back in February. Let's see. There. That's a trick. That's the sorting, conductivity. It's the sorting. Huh? Is there? It's in there. The list of the ions is not there. That's what I'm looking for. Oh, there it is right there. Okay. So this is our list of ions, and you'll have that available for usage. I'll try to get some copies made for you guys that are in the classroom. Those of you at home, where did it go? Oh, there is. That was January 26. Wow. Forever ago. Let's see. I have hard copies right now. Yeah. All right, so those of you at home, let's see. That actually is this one. Okay, so it's actually at the top. So most of the common polyatomics that we need to know. This just has a few others on the back, but that's not a problem. So you do have a copy of this up at the top for those of you at home. Okay, beautiful. All right, now I have to remember what I was doing. Let's see. Treat polyatomics as a whole. Okay. Boop, boop, boop. All right, so the book has this goofy example of making a bicycle. So you have a frame, you have two wheels, you have a handlebar, and two pedals, and you put it together, and you get a, I don't know. So one frame, no subscript, two wheels, you put a sub two, handlebars, two pedals, sub two. So cute, cute, cute. You have to have all the pieces to make your product, okay? Reactants on the left, ingredients on the left, parts on the left, product on the right. The coefficients will often, but not always, become subscripts on your final product. Okay. Let's try this. What the heck? Wasn't planning on the. What time are we doing? We're doing pretty good. Let's do a little practice. Propane gas reacts with oxygen to produce water vapor and carbon dioxide. Which is the correct word equation for this problem? Sorry. Kennedy, what do you think? Is it D? It is. Good job. Which of the following, excuse me, is a skeleton equation? There we go. Got it out of my eye. Emma. It's not D, right? Because those are words.
Yeah.
Okay. It is. Nicely done. What coefficient for H2SO4 is required to balance the following? Uh-oh. I'm going to skip that one because that's a little too soon for doing that.
Wow.
Nice job. I was going to skip it, but James beat me to the punch, man. Good job. All right. Congratulations. Woo. He's on it. So, yeah, we'll go into balancing later, but good job.
Jesus got that one down.
That's awesome. All right. So the other item that you should have in your classwork is the lab. So let's take a peeky at that. Oops, what did I do? Did I not open the lab? I guess not. So we're going to learn the 6 basic types of chemical reactions. Now, a lot of the stuff you see online and on YouTube, they say there's 4. And our book actually only lists 5. My 6th one is a special kind of one of the 5. So I'll explain that as we go along. There's lots of bits and pieces. And again, each day we're just going to do a couple of the reactions and talk about what type of reaction it is. And then use certain things. We will have to use our burners for a couple of them, and test tubes and all sorts of things. So there's 6 basic types of reactions, according to Mrs. Skutches. The book only says 5. And you can look at them in your textbook if you want, but we're going to go through them each day. Terms that you may have heard, I've said them in class, endothermic and exothermic, and I believe they mentioned it on the video. Endothermic, the energy goes into the products. Exothermic, the energy is lost when the products form. Okay, it goes out. So exo, like exit, goes out of the chemicals. Okay. One of the things that happens in a chemical reaction, the reason why a catalyst works is if we look at the energy involved over time, there's a certain amount of energy in the reactants, and there can be a certain amount of energy in the products. Okay, all reactions to get started require something called activation energy. They need a push. So even the most explosive reactions, like hydrogen and the Hindenburg, they need a little spark to get started. Okay, so it has a pretty low activation energy, but everything requires some input of energy to get going. Okay, depending on where the products end up, if they end up with higher energy than what you started with, that's endothermic. If they end up with lower energy than when you started, that's exothermic. But all of them require some input of energy. And what a catalyst does, as it says here, is it just lowers the bar a little bit. Okay, it makes the activation energy. They form intermediary compounds that make it easier to break apart the reactants. Okay, and the difference in energy in the reactants versus the products is what determines whether it's exo or endothermic. So again, this would be endothermic because there's more energy in the products. So that's, woo, has to take it in. Endo means in. Okay, and then exo, the products have less energy. So that's an exothermic reaction. Most reactions you've ever seen, there's very few endothermic reactions that you will observe. That one example was vinegar and baking soda, but that's about it. Okay, all right. And then another thing that we're going to talk about is concentration. The concentration of each reactant is indicated with something called molarity, and we're going to run out of time, so I'm going to stop there, but we'll talk more about this concentration thing when we look at the 2 types of acids. We're going to use 1 molar and 6 molar hydrochloric acid, and we'll go over how that's determined. It's something called molarity. It's just a way to measure what we call concentration. All right, so, and then there's some things that we're going to do to test for gases, but I'll go over that with you. Oxygen, carbon dioxide, and hydrogen are the gases that we're going to form in this. And we're going to use wooden splints to determine the presence of the gas. And we'll go over that, like I said, tomorrow. So the first reaction we're going to do is with hydrochloric acid and calcium carbonate. And then we're also going to do one with hydrochloric acid and sodium hydrogen carbonate, otherwise known as baking soda. And that'll probably be as far as we get tomorrow. And then next week we'll work on these other ones. All right. Questions right now? Okay, we're going to call it good for today. End a little early. And because I don't want to, I don't know if I'll get all the way done with this in other classes. You guys always seem to we get done faster than later in the day. So I'm going to stop recording. Any questions I can answer?